Hi all, I'm Aman and welcome to this series of lectures called Unconstrained Optimization. This is the second lecture in the series, and this lecture is called Mathematical Background Part 1. Before we start with the lecture, let's recall what we did last time. We introduced the topic of unconstrained or optimization in general. We did some definitions, what are optimization, what is a mathematical program, etc. We looked at some example problems, and we also looked at how to formulate the problem for them. And then we looked at the how to solve a few of the problems using graphical solution methods. We realized that in graphical solution, if the dimension is or the optimization variables are more than 2, it's very difficult to visualize and solve it using graphical solutions. And we also looked at some of the references books that you could follow for this course per se. Today we will be going for the mathematical background. So we'll brush up a few mathematical topics that you should be aware of or should be good at for doing good in this course. So we'll first look at a preliminary set theory. We'll look at some concepts of linear algebra. And these two we'll look today in part 1 lecture, and this will look into the part 2 lecture of the mathematical background. That is the analysis and multivariable calculus part. We'll look in the next lecture. Today our goal is set theory and linear algebra. So to let you know, this will be a brush up of these topics. So most of the topics that I'll teach you might have already known or heard about. And this will be a brush up and I hope to solve all your doubts in this lecture. So before starting, it will be in this course we'll have definitions, examples, and maybe some properties of the terms that I'll do. So this is the structure that we'll look into. This is how we'll go on defining various topics in set theory and linear algebra. So with that, let's start with the course. So first, we'll define what are sets. So sets are you already know this. A set is a collection of objects satisfying some property. So, for example, if we have to give an example for this, so natural number, set of natural number is can be called a set. Set of real numbers can be called a set. There is also something called empty set, which contains it's 20 by pi, and it contains no element at all or no objects. It contains no objects. It is called empty set. Then we can define some set operations like union. So this is called a union. You already know this, but so A union B is basically X, such that X belongs to A or X belongs to B. So here this symbol is known as belongs to. You can read it belongs to. So this is what is. So if X belongs either to A or B, then it belongs to A union B. Now let's go to A intersection B. It's called intersection, and it can be mathematically written as X is that X belongs to A and X belongs to B. So it should belong to both A and B, then it belongs to A intersection B. Now, one thing is a difference. So this is called difference, and it means x such that x belongs to A and x does not belong to B. So this symbol is like fairly obvious. This does not belong. So if x belongs to A and x does not belong to B, then x. So if we look at some Venn diagrams, let's say this is A, this is B. So this represents A union B. This area represents A intersection B. Let me just write it down. Yes. So this is A union B. This is A intersection B. And A difference B is parts that belongs to A, but so parts that belongs to A but does not belong to B. So that's what it means. So we can that means this part. This is A difference B. Okay. This we have defined set theory, set sets and set operations. Let's define now subset. What are subsets? So this also you know. So so what are subsets? So let A and B be two sets. So is a subset of B if for all members of A belong to B. That is and it is represented by a symbol A subset equal to B. Now this you already know, so I'll not go deep into it. It's fairly obvious. Now A is a strict subset. So above it was subset. Subset if A is a subset of B and there exists, so I'll write it, but there exists a Y such that Y belongs to B and Y does not belong to A. So there is a member in B that is not in A, then A is the strict subset of A and it is represented by A subset of B. Okay, I think that is that suffices what strict subset and strict subsets are. And we'll define something called Supremum and Infimum. So this will be quite useful in when we'll be studying optimizations in detail. So it's better to define it right now. So just by name, you can decipher what it means. So I'll go ahead and define it. So set A uh, of real numbers, let's say, is said to be bounded above if there exists a number y. So this symbol is there exists. Now a number y such that x less than equal to y for all x belonging to A. So all members of A are less than y. Then we can find a number y such that all members of x are less than all members of A are less than y. Then A is said to be bounded above. Now, how can we use this bounded definitions to define supremum and infimum? So the smallest possible number y satisfying x less than equal to y for all x belonging to A. The smallest possible number. So this is the key. Smallest possible number y satisfying x less than is called supremum. So this is its definition. It's also sometimes called least upper bound. Okay, so and how it is denoted? So it's denoted by y equal to so x belongs to A. This is how it's denoted. Similarly, we can define what is infimum of A. Now, based on these two definitions, it's fairly obvious. So, the greatest possible number by satisfying. So will it satisfy x greater than or equal to y when x belongs to A? So, if this is the y satisfying this, then y is called infimum of A. This is called greatest lower bound. And it is how is it represented in similar way. Y equal to inf x such that x belongs to A. So this is how we define infimum and supremum. So let's look at one example. So let A equal to x belongs to R such that or x belongs to R and x is less than equal to 3 and greater than equal to 1. Okay, so this is set it. So what is the in supremum? Or write like this. So x is belongs to A. What is a supremum? It's 3. And we can see that 3 does not belong to A. So it can happen that infimum or supremum may not belong to the set itself. You can also see we cannot have any number lower than 3 which can be called supremum of this, because any number that you choose which is less than 3 will have a element in A which is greater than that. So 3 is the supremum, and let's see what is the infimum. So infimum here will be correct. So, and we can also see that infimum belongs to A. So it may happen that infimum and supremum both belongs to the set of which they are infimum and supremum of, or they may not belong to it. So it's not a hard and fast condition. Now, moving ahead, we'll look at what are vector spaces. Now this, so actually vector spaces, so some of the sets are called vector spaces. And this is at the heart of linear algebra. So this is at the heart of linear algebra. So let me define it first, and then so actually the definition of vector spaces is very long. So first thing I'll write is it has to follow at least 5 properties that I'll be noting down, and that's what define a vector space. So a non-empty set S is called uh, a vector space if so vector space is actually a set. All those sets which follow these properties that I'll be going to list down will be called a vector space. And then I'll also give you some examples, and I'll give you some other examples which are relevant to us in this optimization course. So a non-empty set S is called a vector space if first property for any x comma y belongs to S, x plus y, that is summation is addition is defined, and is in S. What does this mean? Is like addition is defined. So in that set, some binary operation plus or addition is defined, and the outcome of this, let's say x plus y is equal to z. Outcome of it is z. Then, if z belongs to S itself, then this is necessary for it to be a vector space. So this is called addition is defined and belongs to set itself. So addition should map it back to the same set. Also, the addition has to be defined in a way that it follows these two conditions. So x plus y equal to y plus x, that is commutativity, and x plus y plus z is equal to x plus y plus z associativity. So all these properties you might have heard in your school in school mathematics lectures. So basically what is saying, the order of addition should not change the outcome. Addition has to be defined in a way. So here addition you can define in your own way. So let's say we have a set S. Addition can be x plus y in generally, which we see as summation. You can also define it in any another way, but it has to follow these properties. Like the order should not affect the outcome, and which if you are at if you are doing addition in more than 3 elements, then which do you do the addition first should not affect the outcome. So that's what associativity says. Yes. So this is the first property. This whole is the first property. Then the second property is I call it additive identity. What does this say is there exists an element in S which is called 0 such that x plus 0 is equal to 0 plus x is equal to x for all incremental to s. So there should be an element, we generally call it 0, in set S, such that if we do this addition operation with all the members of S, we should get that element back. So if we do the operation with x, we should get x back. So this is called additive identity. Existence. So it should exist. So existence of additive identity. Then there should be something called existence of additive inverse. So for every x belongs to S, there exists a y belongs to S such that x plus y equal to 0. So for every member of X, for every member in S, there should be its additive inverse there, so that if you do an addition operation between these two, you should result in additive identity, that is 0. This is necessary. So in general terms, additive inverse of, like, let's say, the way we define positive or plus, like the way we define the summation operation in our general real number case, the additive inverse is just the negative of that real number. But you can define your operation in such a way that this may not be the case. So yeah, we don't will not use those kinds of vector spaces in optimization, but it's good to know that there are vector spaces in which summation is defined differently, so its additive inverse is also different. Now we come to the fourth property. So this is I call scalar multiplication. So for every x belongs to S and alpha belonging to R. So let's say alpha is some real number. Alpha x, the scalar multiplication, should be defined, is defined, and is in S. So for example, you can define some scalar times x in your own way. You can define it in your own way. In general case, it's just you increase its magnitude by alpha times. It should be defined, and then this alpha x should also belong to S. Okay, so this is what they should follow. Also, there should be existence of a multiplicative inverse. Multiplicative identity property, which says that if I do the scalar multiplication of x with 1 belongs to real number. then I should get the vector back. This is necessary. You have to define the multiplication in such a way that this is satisfied. And then there are several other properties that your scalar multiplication should define. The first is alpha x plus y. This should follow. This is and or alpha plus beta x equals alpha dot x plus beta dot x. So distributive property. Tonight's is much cheaper. Basically, your scalar multiplication should follow these properties, these distributive properties, and we should also follow one associative property, that is alpha beta. Should be equal to alpha times beta. Just to use the processor the system that we use. Oh, that is that and the robot that we the CPU, the system and the robot. Yeah, robot admin. And set up your own stuff. Why do you want to tell them that you use new plan? They will not figure it out. So let it be that from high. This should it should follow these properties. So why do you have to mention that? I had a very ideal question. So let's call this file. So if a set, so basically let me reiterate what I said. So what I said is, like, let's say there is a set S which follows these 5 properties. That is, first is it should it has some summation addition operation defined, and it follows commutativity and associative property. It has one additive identity in it. It also had some additive inverse in it. Then the set S also has some operation defined called scalar multiplication, in which you define if a element of S is multiplied by some real number alpha, what will happen if you define, and that definition follows these properties: this identity, distributive property, and associative property. Then that set is a vector space. Also, elements. Are you checking to last minutes? My use more called vectors. The 1st October is the 1st October. The 2nd October morning is Tuesday. No, oh, okay. Now I hope that is clear. You can revisit those notes again to know what to just see to like have a pretty clear understanding. But this is taught in every standard linear algebra course, and you can maybe refer to those courses as well. Or the references. These are given in the references that I have told you about. Now, let's give some examples of vector spaces. So first, let's look at a set of real numbers. All these are is it a vector space? You think it's a vector space? So it turns out that, so if we define positive as a plus b, it exists is equal to c, then c belongs to R. This is true. It also follows all those properties that we shows of additive associativity, commutativity. It also has an additive inverse identity of 0, and for every element A there exists a minus A. That tells you that is additive inverse. Also, a scalar multiplication follows all those properties that we saw above. So actually, uh, it's a vector space. It's a vector space. Okay. So is a natural number a vector space? So as it turns out that if you define positive as the sum of two numbers, like 1 plus 2 equal to 3, like this, if you define summation, then it's not a vector space, because there is no additive inverse. 0 does not belong to natural numbers, so there is no additive inverse, and hence this is not a vector space. Similarly, other examples are R square. So R square is a vector space. It follows all the properties that we saw above. Even R cube is a vector space. And in general, any vector uh, of any real number of dimension n set is a vector space. That is. I hope that gave you a decent amount of understanding what are vector spaces. Now let's move ahead. Now, after defining spaces, for after defining sets, we define subsets. Similarly, after defining spaces, we'll define subspaces. What are subspaces? So, just by name, you can guess what are subspaces. So, let's say, so I'll write the definition. If S and T are both vector spaces, such that S is a subset of T, then S is called subspace. So just look at some important points here. So both S and T have to be vector spaces. So if both are vector spaces, that is, both S and T sets follow all the properties that we saw above. If both of them follow that, and S is a subset of T, then S is called subspace of T. So it's not just that if T is a vector space and S is its subspace, S is a subspace of T. No. So both S and T have to be vector spaces. Both have to follow the above properties, and one of them has to be a subspace of a subset of other. Then S is called the subspace of T. So we'll look at some examples and counter examples to see what are spaces and what are subspaces. So we saw that R square is a vector space earlier. Right? So let's try to look at what are the possible subspaces of R square. Let's try to look at that. So I'll just draw R square. Okay. Okay, so let's look at an example. Let's look at all. So both the values are positive. This subplane. Let's look at this. Let's see if it is a vector space or not. So we include these two lines. Include in that side. Now let's take one vector. This is one element. Let's say it's 2, 3. And addition is defined as like uh, so let's say 2, 3 plus 4, 5 should give you 6, 8. So now when addition is defined, how the vector addition is defined. That's how it's defined. Now we have defined addition. Addition also follows the commutative and associativity property. The additive identity is 0, 0. If you add any vector to this vector, you'll get the same vector back again. But what about the additive inverse? What should we add to 2, 3 to get 0, 0? So you should add minus 2, minus 3, which is actually does not belong to the set S. Let's call this S. This does not belong to S. Actually, this S is not a space in general. So it's not a space. So it's also not a subspace of R square. So in general, if you see, if I take any quadrant, it will not be a subspace of R square. Even if I take the upper half or the lower half of this plane, it will not be a subspace. For a plane to be subspace on R square, it has to cover all the numbers, the whole of the plane R square, and only it is possible. So it turns out in two-dimensional, only plane which is a space is R square. So let's look at some. So it feels like for something to be a subspace of R square, it has to be of one dimension, like something like a line, right? So let's look at some line. This is some line. Okay, so let's say it passes through 1, 1, and it also passes through uh, 0, 2. Let's say it passes through 0, 2, and 1, 1. This is a line. So is it a vector space? So the answer is no, it's not. So why is that? So one very obvious thing is there is no additive identity. 0 does not belongs to this line. So there is no number to which if you add the vector, it will give you back the same number. There's nothing. Also, if you see, if we define addition, let's say this is the vector first, this is the vector second. So what is their addition? This is their addition. This is let's call this A, let's call this B. This is A plus B, which will be 1, 3. And actually, if you see, this does not belong to the line. So actually, it does not follow the first property itself. So this line is not a space. As it turns out, you'll see that for a line to be a subspace of R square, it should pass through the origin. So let's say it passes through origin and 2, let's say it passes through this point. Is this a vector space? As it turns out, if we do addition, we try to add these two numbers, we'll again end up on the same line. Same with all the numbers. There is an additive inverse here, 0, 0, and multiplicative property. If you multiply any vector to some scalar real number, it will just scale and it will stay on the line again. So this is actually a space, and also all the numbers on this line belong to R square. So this is a subset of, let's call this line L, subset of R square. So this can be called a subspace. So let's conclude our finding. So all lines passing through origin are subspaces of R square. There is one more set of subspaces. Let's go one more dimension down. So if we only take a set in which there is only 0, 0, then it actually satisfies all the properties of a vector space. So it itself is a additive identity. So it follows all those properties, and so that is also a vector space or a subspace of it. So singleton set containing origin is a subspace of R square. So these birds are examples of the subspaces. Let's generalize. Let's look at the results for same idea. Use same ideas for finding what are some subspaces of R cube. So one thing we noted that it has to be always passing through origin. Origin should be a part, otherwise there will be no identity. So as it turns out, all planes passing through origin are subspaces. So if you see any vector on a plane passing through origin, you add any two vectors, you'll be there on a plane always. Similarly, all lines passing through the origin are subspaces. Same thing. And singleton set. Is a subspace of R cube. So this here we end the discussion of vector spaces. I hope I was able to give you a intuitive understanding of how to think about spaces. Now moving ahead, let's look at something called spanning set.